Hello, this is our first video for Module 4 on electrophilic aromatic substitution. Talked a little bit about this at the end of class, in-person class last week. So just to briefly touch on some of that, if you recall, some of the nomenclature for di-substituted benzenes, so really ortho, meta, and para apply primarily to di-substituted benzenes in their nomenclature. But you can always refer to two substituents as being ortho, meta, or para to each other as well. As you recall, benzene rings are very stable due to the phenomenon of aromaticity, where electron density can circulate around the ring very happily, like clothes in a dryer, I like to say. So, and you can draw resonance structures like this, where the left resonance structure goes to the right or back again in the other direction. Remember, resonance is an analysis, not a reaction. So this analysis tells us that there are two very stable resonance structures that contribute to the overall low energy of an aromatic ring. Sometimes you see this, it's really gone out of fashion for the most part. You see it in older textbooks more. But the circle sort of represents the electrons circulating around. There's 6 pi electrons circulating around the ring without any break in the extended conjugation. So this reaction is very easy. HBr can protonate an alkene like this. So actually there's protons already there. Get a plus charge here. Secondary carbocation, reasonably stable. Then bromine can come back in and give you the addition of HBr across a double bond. With benzene, no reaction. And that's due to the extraordinary stability of the benzene ring. So, as we might guess, there are strong electrophiles, however, that can draw out electrons even from a benzene or benzenoid type aromatic ring. Important point, Lewis acids, electron pair acceptors, can be very strong electrophiles. And classic Lewis acids from organic 1 and 2 are aluminum trichloride. Maybe you hadn't seen iron tribromide before, but it's similar. Aluminum and iron, both short an octet in these original structures, and so when they complex as follows, and I showed this in class, they form strong electrophiles, and they can halogenate, either of these species or complexes can halogenate a benzene ring in the following way. So these electrons can be drawn out to form a bond to that chlorine, kicking these 2 electrons onto the positively charged chlorine. Makes sense that they want to go that way. Leads to the structure here on the right, and the new bond to chlorine right here, leaving a secondary carbocation there, elimination in some fashion, loss of that proton. You would think actually that proton could almost fall off by itself because of the regaining of the highly stable aromatic ring. Regains aromatic stability. And so we've halogenated the benzene ring as a net reaction, if you see from start to finish. And you can do this with iron tribromide as well. And you would list those conditions in the following way. For example, Br2 to FeBr3, leading to simply that. Okay, so when this was learned, it didn't take long before someone said, wow, if only we could form carbon-carbon bonds this way. And thus, we see Friedel-Crafts alkylation, 1877, believe it or not. Not sure they knew the detailed mechanism entirely at that point, but they mixed things together and got products that they could identify. This is really a slight modification of what we saw above. Here we see the complex that's formed between aluminum trichloride and methyl chloride, right? Or chloromethane. So this would be your reaction conditions. If you see this reaction conditions, you want to think this complex being formed. Recognize what you're seeing. The arrow pushing's identical. So new bond forming, bond breaking, and that's a new carbon-carbon bond forming right there. Big deal. I mean, it is a big deal. So elimination in the similar manner, loss of proton, regaining the aromatic system. We have alkylated a benzene ring. We formed a new carbon-carbon bond. And this opened up worlds of new molecules. Because, if you think about it, that methyl group could be substituted with any number of different R groups, almost an infinite number. So, for example, we have this R group right here, attached to chlorine. This is going to form, as we would expect, this complex Cl, Al, Cl3 minus plus, and the carbon to which a new bond can form then is right here, right? So same arrow pushing, bond forming, bond breaking, creates this new bond right there. Elimination, you get the final product. And look at this nice alkyl group we've added on here. You can do the same kind of thing with iron tribromide, just to recall. So, oops, excuse me. So I'll draw the complex that forms here. Br, Fe, Br3 minus plus. Same arrow pushing. Now that we've seen it several times, formation of this new carbon-carbon bond. And if you want, it's helpful to number carbons so you don't lose track. 1, 2, 3, 4, for example. 1, 2, 3, 4. 1, 2, 3, 4. Didn't lose any carbons. It's easy to lose carbons or add them, but easier to lose them. Elimination. There's our new alkylated benzene. However, all is not perfect in this world of Friedel-Crafts chemistry because there are competing processes. So let's say you wanted to do this process where we create a new carbon-carbon bond here, and you would think that these reagents would do the trick. Well, that would be the hoped for product, and you probably do get some of that product. Maybe even half of what you get is that product. However, you get this additional unwanted product. And let's do our numbering again. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So I hesitated there, right? But we'll see, take a look at what comes out. So how did that form? A new carbon-carbon bond right there. So if we look at the complex that is formed, as expected, we notice that there is a process that can compete, which is a hydride migration right here. Hydrogen migration. So that hydrogen with its 2 electrons sort of pogo sticks over, kicks off these electrons onto the positive chlorine to create this secondary carbocation. And let's see if I did number correctly. It's not really a big deal. 1, 2, 3, 4. And 1, 2, 3, 4. So yes, I did, I think. So a secondary carbocation, I mean, we don't think of them as the most stable because they're not. Tertiary carbocations are. But stable enough to form. In fact, we've seen them forming all along on the benzene ring. So this secondary carbocation can form. The benzene ring can go and straight away form, and the carbocations are strong electrophiles. They have a full positive charge. So we form a bond to that, and then following an elimination step in the same way, 1, 2, 3, 4, we get this unwanted product. So you're going to get a mixture of products. In order to address this will be the start of our next video, Friedel-Crafts acylation as a way of solving this. And in fact, I mean, it does introduce an extra step potentially, but it also opens up possibilities of even more new reactions, as we'll see.